So now we have done the moment curvature analysis for a particular section for one level of axial compression, which is your 0.1 F prime C AG. Okay, so this is what we did previously. Now let us see if I increase my presence of axial compression, the P that what we have put instead of 0.1 F prime Cg. Now if I am putting 30%, if you go back, what is that corresponds to P is equal to 0.3 F prime Cg is going to be zero point 0.3 multiplied by 40 multiplied by 400 multiplied by depth of 600. So again, if I divide by 1000 to get it in kilonewton, how much we are going to get? 3 times what we got previously. So that works out to be 0.3, 40, 400 times 600 divided by 1000. You get a force of 2880 kilonewton. It's a quite a significant level of axial compression. Okay. Now, if we cannot say that if you keep on increasing P, you will get higher moment resistance. In fact, when the section becomes only when it remains tension controlled, then only this. So that's why we said when you are increasing up to a certain extent, you will get increase in moment capacity and increase in your stiffness. But otherwise, if you put too much compression, then it will fail in compression. It will become compression control failure. Then your moment capacity will not increase. In fact, it will fail in a very brittle mode, which we don't want. Okay, so that we have to be careful. Anyway, in this case, now we are going to apply an axial compression of 2880 kilonewton. Now let us see what we are going to get. So this is the results that we got for P is equal to 0 from example 5.1. Now this is for example 5.4. So we have set. So 68.1, I called it, I used 70 value as a round value to show you the comparison, but also moment resistance we got about 316 or so. So you see here, the moment resistance has increased from 316 to 524 due to the axial compression. Now the curvature has reduced from 68 to 26.18. So we have seen it in the moment curvature plots also. Now let us see what happens when your axial compression is increased from 10% of concrete capacity in compression to 30%. Okay. So in this case, I am putting P is equal to 2880 kilonewton. Now I am just showing only for one value of top fiber strain of 0.0035. That is your ultimate strain for concrete in compression. So, and I have taken iteration and then I have got my X value as 298.3 millimeter. So now again from your strain conditions, you know that from similar triangle, you can get your epsilon t and this distance you know which is equal to t minus x, right? So and this is x, right? So this v is x. So from your similar triangle, you can get your epsilon t as 0.0030 and it is greater than strain of. So you see here, at when concrete reaches 0.00, steel has yielded. In fact, the steel has just gone above 0.002. I mean, just it has yielded. Okay, and it is not stretched too much. Okay, so what is the significance of this? Still, the section is, even though I am putting an axial compression of 2880, still the section is tension controlled. So how do you say the section is tension controlled? When concrete reaches its failure strain of 0.0035, steel on the tension side has yielded. Okay, it is just yielded. So in fact, this is close to a very close to a balanced condition. Okay, because the strain in the steel has slightly increased more than 0.0025. Okay, so anyway, tension force now because this is there, Fs is going to be 500. We know that. Okay, right. So if you substitute Ts, you get and again the force, the tension force P plus Ts from your force equilibrium because P is again acting from left to right. Ts is also acting from left to right. So they all in the same direction. So you add them up and you get a force of 3480 kilonewton. And now again for epsilon c equal to 0.0035, beta 1 is 0.9, alpha 1 is 0.81. Then how do you get your cc? Again we go back, alpha 1 f prime c, beta 1 x multiplied by b, that is your cc. So you substitute all the values and you get a force of 3479.4 kilonewton. So you see here again I am satisfying the force equilibrium. Cc is equal to P plus Ts nearly. So the assumed inertial axis depth is correct? Then we go ahead and uh, check your moment capacities. Again, moment capacities, we are going to take about this CG, this point. So you're going to have counterclockwise, you're going to counterclockwise. So both of them will add up. And you previously we have done your lever arms. Okay, let's say we call that as Z1 and Z2. Now Z2 is what? It is basically d minus h by 2. Okay, this distance. Z2 is nothing but d minus h by 2. So what is Z1? Again, it's going to be h by 2 minus beta 1 xu by 2. Okay, so we have done that. So if you go back moment about depth, so this is what it is. Here I've taken d and h are same. Okay, I've taken d is equal to h. Okay, both are same. Okay, so if you do that, you get a moment resistance of about 726.9 kilonewton meter. And if you do the curvature, you get a value of 0.0035 by x, which is 298.3. You get a curvature of 11.7. Is here again, if I put more compression up to zero point 0.3, then I get a higher moment capacity. However, the curvature is reduced from 26 to 11.73. So if you plot, if you do the analysis for multiple points like point triple zero, we have just shown for 0.0035. We got this and we got this. You can do the same process what we have done by incrementing your epsilon c. Again, by using different xu to satisfy equilibrium, and then you get your alpha beta, and you take your moment and calculate your curvature. These are the values that you're going to get. Okay, for zero point 0.3 f prime CAG. So if you start plotting, now let's compare the three different cases that we have discussed. Okay, when p is equal to 0, we have got this. So you got about 310 or 16 or something like that. Okay, so that is the thing, and it failed at about 70. Okay, the moment I put 780 kilonewton, the moment curvature capacity increased to 520 or something, but curvature at failure it reduced to 26. Okay, now when P is equal to zero point 0.3 F prime CAG, which is a quite a bit amount of compression, 2880 kilonewton, you see that the moment capacity now has increased from 520 to 720 or so. So good amount of increase that you got, right? So what we can see here is the moment capacity starts increasing and curvature capacity starts reducing. So, but this is valid. We have done the analysis only for P up to 0.3 FMC. If I keep on increasing P, this we cannot say that you will get more moment resistance and reduction curvature. In fact, the section, when the moment the section becomes compression control, your moment resistance will reduce. Okay, which we will see in your when we do the column analysis, when chapter on understanding the behavior of columns, there we will see. But here, if you start plotting your moment resistance with respect to the level of axial compression, so this is what it is. Up to 0.3, you get increase in your moment capacity. The moment you put more than 0.3 for the section that we have considered, okay, you see that the moment resistance starts reducing because we have done the calculation for 0.4 and 0.5 also. Okay, so this is the plot. Now, similarly, the curvature, you can see that when you have low axial compression, the curvature is I am plotting it in the secondary axis. Okay, so you have to see from curvature point is, if this is the curvature means this is the value. It's about 70. Now, when you have p is equal to 0.1, you get a curvature of 26, right? Then similarly, when p is equal to this, you get a value of about 11 or so. So that's what we're getting here. Okay, so what is that we can conclude from this is, when your axial compression is less than about 30% of your compressive capacity of concrete, then we can see that when you increase the P, there's going to be an increase in moment capacity, and also there's going to be a reduction in your curvature. Anyway, with increase in P, you can say that the curvature at failure is going to reduce, or the section is going to become more brittle. So when P increases, the moment capacity increases up to zero point 0.3 F prime C Ag, and when P increases, curvature decreases, or the section becomes less ductile, right? So if you have to summarize whatever we have discussed in this module, we have discussed how to carry out moment curvature analysis for flexural sections with axial compressions, and we also discussed what is the effect of axial compression. Okay. If you're able to put some axial compression at a lower level, then it is very beneficial in terms of increasing the moment capacity. It's like similar to putting more amount of steel on the tension set. So for a single reinforced section, we saw in the previous model, more the steel you put, more moment capacity you get up to the level of balanced condition. Similarly, same P also, you can keep on increasing, you'll get more moment capacity until the section becomes compression control or until the section becomes balanced. After that, it is not going to help. In fact, it will be detrimental, putting more axial compression. So the other things that we will discuss. So thank you. I will continue the discussion in the next module.